Okay. So consider this example where we're being asked to use the method of sections to determine the axial force in the member EF. So the first thing we want to do here is to identify where EF is. And in this case, EF is this side, just somewhere there. So that is the member which we want to analyze. And by the axial force, they're asking us to find the internal force inside the member EF. Okay, so having identified the member EF, now how do we determine the internal force inside that member? Now, well, there are a number of ways we can approach this. In one of them, as we were discussing, or as you have seen under the method of sections, is that sometimes we want to first account for the reaction forces at the supports. In this case, we have that support and one reaction there because we are seeing that as a pin, not as a pin, as a roller because of the small wheels, which are at the bottom right there. See the difference? Here we're seeing this, the way it is connected. Here we're seeing the way that is connected. So this is why here we claim that this is a pinned connection, or this can be seen as a roller kind of support. But in this case, the section I will select is going to be an upper section. And for the upper section, we will not need the reaction forces. So we're going for the member EF. So I'll section it somewhere here. And if I pick that, that demarcation and just focus on the upper part does not require me to know the reaction force this side. So if I just focus on that, then I will not need to know the reaction force down. So let's go with that. Based on that selection, let's try to work out what the force EF is going to be. Well, we might not be able to get EF directly, so we might have to find a few more members, sort out a few more members before we go anywhere towards EF. So let's redraw that structure, the section we have selected, that is. Okay, so having made a redraw of my selected section, so I've just drawn the same structure, but observe that I've only drawn it up to here. And then the dotted line here just indicating that E continues all the way up to F, which where F occurs there. And the other side, E continues all the way up to G, but I'm not really including that part. Now, from here, how do we sort out this part? Okay, so we know how the method of section works, having looked at it before. We have selected our section, and in this case, the exposed members now, the forces inside those exposed members now become external forces. So when we try to sum forces or take rotations, those forces will play a role. The concept of equilibrium, as you might remember, is that if the whole structure is in equilibrium, even when we cut a section of this structure, the selected section or either section must still remain in equilibrium. The only way this would be possible is if we expose the internal forces after having sliced this into two sections. So we have the internal forces in this case. In this way, I am just assuming the sense in each member. And you recall that if I find any of these forces to be negative, it will imply that the forces are actually in the opposite direction. And under the method of sections, again, recall that these forces are not necessarily being applied at the joints, but they are describing the internal forces inside the member. In other words, this force FED, or let me say this is DF, the assumption is that this is compressive. Actually, for all the members here, I am assuming that they are all compressive. So this is EF, and this is FEG. So the assumption here is that all my members, that is the member DF, EF, and EG are compressive. For this question, the one they're asking us to find is just EF. So the other two are just going to be necessary because by cutting through F, those two end up showing up as well. Now, how do we work out this question? Well, there are several methods that we can use, but all you want to keep in mind here is that you have to use either sum of forces equals to 0, or sum of rotations about any point being equals to 0. You want to try sum of forces if it works, but whenever you have angles involved, like forces not being strictly y-axis and x-axis, sum of moments might be preferred. Now, how do we proceed from here? So the first one that we're going to find here is going to be, you can use either, of course, here, but for starters, I will go towards finding first FDF there. So how do I find FDF? Well, I am going to take moments about, we can take moments about this point here, about point E. You can start from anywhere, really depending with what you're trying to find. But if I take moments about point E, notice that it is going to eliminate the force EF because EF passes through the point E, and it is also going to eliminate the force EG because that also passes through that point. So doing this eliminates two of the unknowns there, leaving me only with FDF. Here, of course, I am just working out as I would try to find all the three exposed members there, so that you guys find a way of practicing while we're doing this. Okay, so taking moments about E, so let's sum moments about E. What do we see there? Well, firstly, the 10 keep here, the 10 is acting in this direction. Based on that, it is causing clockwise rotations like that. So it is going to be negative. So you have negative 10. But what will be the distance? Here, the distance will have to be from here to there. That is going to be the perpendicular distance. And according to this, from here up to that, this is given as 4 feet. So because of that, this will be multiplying 4. Next up, we have the 10, which is on top as well. This is going in that direction. It is causing clockwise rotation, so another negative. The distance will be the first 4 plus the second 4. So that is going to be 8 in this case. So you have minus 10 multiplying 8. What other forces are appearing here as external forces? We've already seen that these two, even though they are showing up as external forces, they won't cause rotation about E, so won't consider those two. But when you look at this one, however, this one is an external force in this case, and it is causing rotation about E. But the distance we have to use is going to be this distance here. And that force is FDF. So that is FDF. What kind of rotation do we expect? It's downwards, so we're expecting it to cause an anti-clockwise rotation about E. So we have positive FDF. But what will be the distance here? So for the distance, you have to use the original diagram, and you kind of have to more like pay attention to what is happening. You can do it the easy way or the hard way, whichever way you choose. If you want the more mathematical way, you can take the fact that from here all the way up to the base here, it's given as 4, 4, 4, 4, which is basically just 16. And from here up to here, this is given as 12 there. So 12 in this, you can use the 12 and the 16, which is vertical, to predict what the angle is going to be for this blue triangle. So you can figure out what this angle here is going to be. So since you're going to know what that angle there is going to be, you can then consider this red triangle, which is going to have that line DE. So the red triangle, now you can look at it from here to here and to there, so that it has this base here, DE. Now DE here, since you know what from here to here is, that's just 4 and 4, which is just going to be 8, and this angle remains the same, you should be able to find what DE here is going to be. But based on symmetry and how this is what is given here, you should see that DE will have to just be half of BI here. Since BI was given as 12, we expect to find DE here also to be just half of that 12. So in this case, the distance from D to E, again, you can do it the mathematical way, but you should see that you will find it to be half of 12, which is just going to be 6. With that in mind, once you find that the distance from here to here is 6, notice that you can now multiply FDF with that 6 to get the moment of FDF, about E. So this will multiply that 6 feet. So this will have to be equals to 0. From here, we can do the math, move everything else to the right-hand side. You remain with only FDF. Of course, I will divide also by that 6. So you're going to have 10 by 4. This is going to be 40 to be positively on the right-hand side. And then 10 by 8, it's going to be 80. Again, this is going to be positive on the right-hand side, but you have to divide this by 6. So this is basically just 120 divided by 6. This becomes 20, and the forces here are given in that unit. Since FDE came out to be positive, the assumption that we made earlier on is going to hold. It was correct. So we assumed that all the members were in compression. So FDF, was stated to be 20 kip. And the sense here is going to be taken as compressive. So with this, we have found what FDF is. Okay, having figured out FDF, now we have to figure out the rest, and don't forget our target is FEF. But in this case, of course, we want to find just everything there. So the next one that we'll try to work out here, again, completely up to us, but the easiest one that we can find here is going to be FEG. So let's try to find FEG. How are we going to find the force FEG? So for this one, what I'm going to do is I'll take moments about the point F. We can take moments about anywhere really. According to the conditions of equilibrium, it's the moment about any point which has to be equals to 0. So for this one, I'll take moments about this point. Why am I choosing that point? Because in this case, we observe that the force EF does pass through that point, so that eliminates that unknown. Then also, this force passes through F, so even that force will not have to be considered. So in this case, the only unknown that will cause a moment about F is going to be EG. The only tricky part here will be expressing EG as in its components so that we can easily evaluate what its moment is going to be. Now, how do we do this? Well, firstly, let's start getting the moments. So when we sum moments now about F and equating to 0, we see that the 10 here at A and the 10 at B will still be causing moments about F. So in this case, moment about F due to the 10, we see that they are both causing clockwise rotations about F. So they will both be negative. So we have negative 10 here. But what will be the distance from F? So from F going all the way up to, that's from F going all the way up to A. Let's just start with up to B. So the distance there is going to be the 4, and then the 4 there as well. So this is going to be 8. So you see that here, the distance is going to be 8 feet. Then minus the second 10, the one acting at A. But to A, the distance is going to be 4 plus 4 plus 4, which is 12. So here, the distance is going to be 12 feet. Then the only other force causing a rotation about F in this case is going to be the one in that member, EG. But we need to express this strategically so that we can easily evaluate its moment. But how do we do that? Well, we want to represent that force into its components so that the distance will be easy to represent. But how do we do that? Well, the concept here is going to be very, very simple. We're going to use the fact that you already know what this angle here is. Okay, so we can actually find it. Remember, I did show you how you can get that angle if you need to find it. But let's quickly just go through how you get it. We did point out that for the larger structure, the whole structure, what we have is that the vertical part is 16. I'm saying 16 based on 4 plus 4 plus 4 plus 4. So the whole structure here has 16, the vertical that is from A to H, that's 16. Then from B to I, we have, is that 12? That's 12 from H to I, that's 12. So with this, we can easily get what this angle here is. Let's label it as theta. So you see that theta is going to be tan inverse of the opposite, which is 12, over the adjacent, which is 16. So what is this going to give us? Can you do this? What angle are we going to get there? Okay, 36.87 degrees. So once we have that angle, you have to see that if I was to draw a vertical line right through E there, notice that the angle here would have to be the same as the angle here. Why? It's like, let me just remove these lines for now. If you have, this is AH, and then we have this straight line here. If I was to draw another straight line, but now at, which point is that? At E. So this is A. Here we have that angle that we just found as 36. It was 36 point what? 0.87 degrees. Another straight line drawn here implies that even this angle will also have to be 36.87. So this is the logic that I am trying to use there. So this is the angle we are going to use to break down this force here. Since we're saying that a line drawn here ensures that the angle here is the same as the angle there. So having found this angle, we can relate it to this one, then use it here to break down the force FEG into components, into a horizontal component and a vertical component. So with that in mind, we can look at FEG and say that since FEG makes an angle of 36, let's just say theta there, we can easily get its horizontal component and vertical component. The vertical part is going to go down like this, and the horizontal part is going to go to the right like that. So the one going to the right will be FEG, then sine that angle theta. Is it EG? Let's verify. Yes, that's EG. And the one going downwards is going to be FEG, but this will be cos theta. So this is how we're going to get those two components. So let's now look at them and see what type of moments they will be causing. So I will remove that theta. It has saved its purpose. You don't need it anymore. So where am I? So here, when it comes to, I'll evaluate the moment due to FEG by its components. So I'll start first by the X component. So the X component, we saw to say it's pointing to the right. So if it is pointing to the right, what type of moment is it causing? They are all acting at E. So the X component of FEG is basically acting at E horizontally to the right, like this. Based on that, what type of moment is it causing? Its line of action is this line. So it is causing a clockwise rotation. So that is the X component. So based on that, we conclude that the X component here is causing clockwise. So we have minus, and it's FEG. And as you saw earlier, it is FEG sine theta. So we have sine, and our theta is 36.87. Is it? Yes, it is. Yeah, so this is just the X component. But what will be the distance? The distance has to be from F to the line of action. F is here. The line of action, as you saw earlier, is up to there. So what is the distance from F to D? From F to D, this distance is just 4. So that is going to be the distance we use there. So multiply that by 4. Just don't make a mistake of multiplying this with the 36.87. Multiply it with the whole sign that. Having done that, we then move on to the next part, the Y component of FEG. The Y component of FEG will also be acting at F, at E I mean, but it will be acting vertically downwards. So the distance here is going to be this distance. And remember, we already used it. It was basically the distance from D to E there. And we saw it was 6 feet. So this is going to be the force itself. Let's reduce the size here. Okay, so the force itself is going to be, so observe that this is also going to be it's going to be clockwise. So it's going to be FEG, but now we're going to have cos 36.87 and put brackets here. And this is going to multiply 6 feet. And that is the last one. So this is going to be equals to 0. So at this point, just try to now work out this for FEG. I'll take everything that doesn't have FEG to the right, leaving us with just minus FEG sine 36.87. I'll write the 4 face so it doesn't confuse us. So you have minus 4, then you have FEG sine 36.87. Then we have minus, now the 6 again, FEG, but this time it is cos 36.87. So this is these two here. So just make sure I am not making any errors, just copying those. And then the 10 multiplies the 8, goes the other side, becomes positive 80. And the 10 multiplies the 12, goes the other side, becomes positive 120. When you add these two, you see that you just get 200. So this is what you're going to get there. So from these two, the first two terms, factor out FEG, then divide it the other side. So you get FEG is equal to negative because these two are negative. So you have negative there. This will be 200 divided by 4 multiplying sine 36.87 plus 6 multiplying cos 36.87. So this is what we're going to have to give us FEG. Can you try to do this? What are you going to get there? Okay, doing it. You see that we get 27.7. So let's just say 27.8. In the units here, we have the kip. So because this has come out to be negative, and our assumption was that it was compressive, so this implies that our answer is actually 27.8, but instead of compressive, this has to be tensile. So see how I keep changing depending on how the sign comes out there. So once we have figured out this one, now the only one that is left is EF. Now, how do we find EF? Well, to find EF now, we can use either the sum of forces or the sum of moments. So either one now can work. But which one will be the easiest? Because you always want to use the easiest method. Okay, so now figure out what is happening to EF, to the force EF. You can use either approach sum of forces, sum of moments again. I will just look for the easiest one or the first one that comes to mind. But regardless of what we're going to use here, clearly we will need to know the components of EF. So when you look at EF, EF is acting something like this one here. So this is the line of action of EF. It's running all the way from E coming to F. Now I will just complete the triangle here so that you see what sides I will use there. So we'll take this part to be F, to be DF. And then we have this horizontal part, which is DE. Remember, we already found what DE was. DE was 6. And the vertical part, DF, we go back to the diagram. DF is from here to here, and DF is given as 4. So since we already know DF and DE, this is what we have. Notice that with these two, we can easily figure out what this angle here is. Let's label this angle as phi, and then we can use that angle to break down EF into parts. So if we wanted to find phi by tan, this is going to be tan inverse, and it will be tan inverse of the opposite, which is 4, over the adjacent, which is 6. So what are we going to get when we perform tan inverse of 4 over 6? What are we going to get there?
I'm getting 33.69 degrees.
33.69 degrees. Okay, so we get that is, you said 33, right?
33.69 degrees.
Okay, great. So phi there has come out to be 33.69. So having found what phi is, we can then use that angle to break down our force. So our force, remember, is acting in this direction. That is our force FEF. So in the first part, I was using the sides to get the angle there. So now I do not want to look at the side. Instead, I am bringing back the forces. So using the forces now, I am saying that this red line is my FEF. So it's acting in that direction, and the angle here is this 33.69. So with that known, I can now use that force to get the components. So the X component will be going to the left in that way, and the Y component will be going vertically downwards in that way. And of course, by sine and cosine, we can easily evaluate what these are. So FEF, the X component will be FEF, and seeing that it is side by side with the angle phi, this will be given by cos phi. And the Y component will be FEF, and this will be given by sine to multiply sine phi. Now, since we now know the components, or at least the expression for the components, we can easily choose which method we want to use to break down this. Now, in this case, which approach is going to be better? If I say I will get the sum of, let's see, if we choose to go with the sum of forces, what are we going to need? For the sum of forces in the y-axis, we need the y component of this, the y component of this one as well. So we need to get the components there. If we choose to go with moments, if we wanted this force here to survive EF, it will imply that we'll have to take moments about A. So moments about A is what we will need there. Is that going to be easier? Well, it will eliminate EG completely because EG will end up passing through A there. And it will also eliminate this one because it goes to pass through A. It also eliminates the 10 keep there because it passes through A. Look at that. The only one we will have to worry about is going to be the 10 keep, which is here, and our force EF. And even for EF, yeah, and our force EF. Those are the only two forces which will cause a rotation about point A. There we have it. The easiest approach, according to what we're seeing here, has to be the sum of moments. And in this case, the sum of moments has to be evaluated about point A to get the easiest approach. Now, if we get this, and let me just copy it. What this actually shows you is that we could have easily found the force through EF without even knowing what EG and DF, what they are, because this approach actually just goes directly, because the forces through EF and not EF, the force through FG, that's FG, the force through EG and the force through DF, they go through A, meaning taking moments about A would have eliminated them, even without knowing them, would have still found what EF is. Let me demonstrate. So if we take moments about A, in this case, only EF will cause a rotation and this then keeps. So I'll remove this because it won't cause rotation about A. I'll also remove the DF there. It won't cause rotation about A. And I'll also remove this. It won't cause rotation about A. The only ones causing rotation about A is 10 keep here and the force EF. So how are we going to work them out? So let's take moments, sum of moments about point A and equate to 0. So about A, we have the 10 keep. This 10 keep, it's going to cause anti-clockwise rotation. So we're going to have positive 10. The distance will have to be from A to B. And if we go back to the original diagram from A to B, what we have, A to B is this one, which is 4 feet. So we're going to have 4 feet there. Then next we have the force at E. The force at E, we're going to express it into its pieces. So that is in terms of components. So the vertical component is going to pass through that. And again, we're looking for this one, which doesn't pass through A. The vertical component is going to pass down like the way this one is here. So if we trace the line of action coming all the way up like that, the distance will have to be this distance. Again, notice that this distance is the same as DE. In DE, we already found that to be 6. And lastly, that Y component will be causing a clockwise rotation. So it will be like that. Based on that, to be minus, and this is going to be FEF. Remember, the Y component of EF, what did we see it was going to be? Going to be FEF sine phi. So having sorted out the Y component, now let's figure out the moment due to the X component. So the X component of EF will be acting at E, but it will be going horizontal to the left like that. I think we already established that. So it will be going horizontal to the left, and this implies that it will also be causing clockwise rotation. Because it's clockwise, it's going to be negative. Oh yeah, here we have to multiply with the distance, and as I mentioned, the distance here will have to be 6, which is the distance from D to E. Okay, now moving on to the X component. So we have already established that it is clockwise, so we have that minus there, and the force itself is going to be FEF. And for this one, we had cos phi. The distance for this one, it is acting through, let me move some of these lines. So it is from A all the way up to D here, which is the line of action of that X component. So from A to D, what are we seeing? From A to D is basically from here up to here, which is 8. So that has to multiply 8. These are the only forces causing rotation about A. So we equate this to 0. Luckily, we already have what the angle there is. So move everything else to the right, leaving us with F. Basically, this will leave us with this part. And then the 10 multiplying 4 will multiply and go to the right, becoming minus 40. Divide everything by negative, or multiply everything by -1. This becomes FEF sine phi multiplying 6 plus FEF cos phi multiplying 8 is equals to 40. Pull out FEF, divide by what will be in the brackets. We see that this will be equal to 40 here. And then this will divide 6 sine phi. We already know what phi is. It's 33.69. Let's